Hi everyone, I'm going to teach you Learning Target 5 of Unit 8, Sequences and Series. Learning Target 5 is I can calculate and use finite, that's part 1, and infinite, that's part 2, geometric series. And remember, from arithmetic series, a series is just a sum of a sequence or adding up a sequence. Part 1. The finite geometric series formula is S sub n, S standing for sum, just like with arithmetic series, equals a sub 1 times 1 minus r to the n over 1 minus r. Deriving this formula is much more involved than deriving the formula that Carl Gauss came up with arithmetic series. So I do have a derivation video if you want to watch and see how this formula came about with patterns, but using this formula will help us find the sum of a geometric series. For example, if I wanted to add these 5 terms of a geometric series where I'm multiplying by 2 each time, I could just add up these 5 terms and I would get the geometric series. But if I wanted to add up, instead of just 5 terms, 50 terms, for example, then I would most likely use this geometric series formula where n is 50. So let's go through 2 examples with this finite geometric series formula. Example 1. Find the geometric series given the information below. A sub 1 equals negative 2, r equals 3, and a sub 8 equals negative 4,374. I'm going to write the formula. S sub n equals a sub 1 times 1 minus r to the n, and just r, the ratio, is raised to the nth power, over 1 minus r. I'm going to input the information that they give us. S sub n, and n is the amount of terms that I'm adding up. I see 8. They're telling us that the last term of the series is the 8th term, so n equals 8. So S sub 8 equals, a sub 1 is negative 2, times 1 minus r is 3, raised to the 8th power because n is 8, divided by 1 minus 3. All I have to do to find the series or the sum is simplify. So S sub 8 equals negative 2 times 1 minus 3 to the 8th power, simplifies to negative 6,560, divided by 1 minus 3, which is negative 2. And then when I divide these two values and multiply by negative 2, I get S sub 8 equals negative 6,560. That is my geometric series, or the sum of the sequence from negative 2 to negative 4,374. Example 2. Identify the sum, S sub n, given a sub 1 equals negative 2, a sub n, that last term, is negative 13122, and r equals negative 3. So I'm going to write the formula. S sub n equals a sub 1 times 1 minus r to the n over 1 minus r. I'm going to input the information they gave us, S sub n. We don't know the n value, so I'm going to have to do some work on the side here to find the n value, and I'm going to find the n value by going back in my brain to previous week and using the geometric explicit formula. A sub n equals a sub 1 times r to the n minus 1. A sub n equals negative 2 times negative 3 to the n minus 1. And I'm going to input the nth term that they gave us to solve for n. So negative 13122 equals negative 2 times negative 3 to the n minus 1. To solve for n, I first divide by 2 on both sides. That gives me 6,561 equals negative 3 to the n minus 1. And then I take log base 3 of both sides. And that gives me 8 equals n minus 1. Add 1 on both sides. That is 9. So that was my side work to figure out what the n value was. Now I can input 9 in for n. So let's continue to find the series. A sub 1 is negative 2 times 1 minus r is negative 3. Because it's negative, I'm putting it in parentheses. Raised to the 9th power over 1 minus negative 3. So putting this negative 3 in parentheses will signal to our calculator that we're raising just negative 3 to the 9th power. And then I'll simplify to find the geometric finite series, and I get s sub 9 equals negative 2 times, simplifying the numerator, I get 19,684 over 1 minus negative 3, which is 4. And then when I divide these two and multiply by negative 2, I get negative 9842. That's the geometric series. Let's look at part 2, infinite geometric series. So for geometric sequences, you could have an r value, a common ratio that's greater than 1. For example, r equals 2, right? I'm doubling each time. And that would look like an exponential growth function if it's growing. So if I'm looking at an exponential growth function and I want to add up all the terms of this sequence forever and ever and ever, right? The infinite amount of terms, all of them. Well, because this is exponential growth, it continues to grow towards infinity. So if I add up infinitely many terms in a growth sequence, then my answer, the sum of the infinite terms, is infinity. Done. But if my r value instead is between 0 and 1, then I get an exponential decay function. Exponential decay functions as we approach infinity. So if I add up infinitely many terms, I'm approaching 0. So eventually I'll be adding such a tiny, tiny fraction that it'll be insignificant to be adding that amount. So I actually get a value other than infinity or negative infinity. I get an actual finite value for the sum of infinitely many terms if I have a decay sequence. So the formula, when we were just adding up any finite amount of terms, was a sub 1 times 1 minus r to the n over 1 minus r. The part of this formula that doesn't matter anymore when we're adding up infinitely many terms is this numerator in parentheses. Because if I have 1 minus some small fraction, maybe 1/2, raised to infinity, well, it's hard to think about infinity as an actual number, so if we raise that to the millionth power, this is going to be such a small fraction, a half times a half times a half times a half, infinitely many times, that it's not going to be significant anymore. This will be such a tiny fraction that we're subtracting from 1 that we don't even need to consider it anymore when we're adding infinitely many terms. So this numerator before was 1 minus r to the n, but now with infinitely many terms, it's just the number 1. And anytime you multiply something by 1, it just goes away. So my formula becomes a sub 1 over, so we don't need this part, over 1 minus r. Let's use this concept of infinite geometric series formulas. 3 examples. Example 1, identify the sum of infinitely many terms given a sub 1 is 4 and r equals 2. Automatically I see r is 2, so I'm imagining an exponential growth function. So the sum of infinitely many terms when we have a growth function is infinity. Done. Example 2. Identify the sum of the infinite series given below. So we have 1, 3/4, 9/16, 27/64, ... I know this is infinite because I see the ... and there's no ending term here. To figure what r is, what am I multiplying by each time? And I can see from the first two terms I'm multiplying by 3/4. And if I check that, 3 times 3 is 9, 4 times 4 is 16. Multiply by 3/4, I get 27 and 64. So 3/4 is my r value. And I'm thinking about an exponential decay function, so there will actually be a value when I'm adding up infinitely many terms, because I'll eventually be adding such a small fraction that it'll be insignificant. So using the formula from above, we have a sub 1 over 1 minus r. A sub 1 is 1. 1 minus r was 3/4. So the sum of infinitely many terms is 1 divided by 1/4, which equals 4. So really this equals 3.99999999999 on and on and on and on. But because it's so insignificant, we just round that to 4 using the formula. Last example. Pendulum. Think about those really old clocks. A pendulum just swings back and forth, back and forth. Using gravity, it eventually will stop swinging, but actually continue swinging ever so slightly as time goes on. So here's the problem. A pendulum swinging freely travels 72 inches on the first swing. So one swing, it's traveled 72 whole inches. On each successive swing, it travels 94% of the distance of the previous swing. How far will the pendulum ever swing? So with the information, I'm going to underline those key pieces of information that I have. A sub 1, that was the first term, is 72. And 94% in decimal form is my r value, 0.94. Because this is an exponential decay, I know I'll use the formula. The sum of infinitely many terms equals a sub 1 over 1 minus r. So 72 divided by 1 minus 0.94. And that simplifies to 120 inches. So that's all I have for geometric finite and infinite series. If you have any questions, let me know. Have a great day.